In episode 3, we showed that cross-entropy warps flat plateaus into steep cliffs. The model ball rolled to the global minimum. But the real genius happens under the hood before a single step is taken, the initial error calculation. Let us recall the two functions in play. Softmax converts raw logits into probabilities. That is, the exponential of our logit divided by the sum of all exponentials. Cross-entropy then scores the prediction. Negative sum of the true value times log of the predicted value. That log is waiting for something to be substituted in. Now we substitute. The predicted probability for each class, previously written as y hat, is replaced by the full softmax fraction. Both operators are now nested inside each other in the loss function. Differentiating this nested expression with respect to the raw logit looks terrifying. Applying the chain rule gives two separate terms. One for the correct class j equals I and one summed over every other class. The exponentials and the logarithm are about to collide. Before the terms cancel, factor out the common predicted value term. What is left inside the bracket is y sub I plus the sum over every other class j. That bracket is the full one-hot vector, a probability distribution where all classes sum to exactly 1. So the entire bracket collapses to 1. Negative I sub I plus predicted value times 1. The times 1 drops and we are left with the predicted value minus true value. The gradient at the output layer is simply prediction minus the true value. If the model predicted 0.8 and the ground truth is 1.0, the base error is exactly negative 0.2. This single scalar is the starting pulse of backpropagation. To understand the backward flow, we strip away all complexity. A micronetwork, one input node, one hidden node, one output node. Our goal is to find the gradient for weight 1, buried in the very first layer. The chain rule dictates that to find the total effect of weight 1 on the error, we multiply the isolated sensitivities along every step of the path. Partial j over partial A3 times partial A3 over partial A2 times partial A2 over partial double U1. We work backward. The negative 0.2 error flows across weight 2. If weight 2 is 0.5, the error signal is scaled by half. The error arriving at the hidden node is negative 0.1. We continue backward to weight 1. Its gradient equals the incoming error multiplied by the raw input it received. If the input A1 is 3.0, the final gradient for weight 1 is negative 0.1 times 3.0, negative 0.3. But real networks branch out. A single hidden node simultaneously influences multiple different output nodes. This is where things get interesting. Say our hidden node helped produce a correct prediction for one output, but contributed to a mistake at a second output. That second output sends back a positive error of plus 0.4. After crossing its weight of 0.5, the signal arrives at the hidden node as plus 0.2. Delta A2 from path 3 is negative 0.1. Delta A2 from path 4 is positive 0.2. A node takes responsibility for every downstream mistake it contributed to. We simply sum all incoming gradients. The net signal at the hidden node is negative 0.1 plus 0.2 equals plus 0.1. Multiplied by the input A1 of 3.0, the gradient for weight 1 is plus 0.3. The network perfectly balances its conflicting demands using basic addition. We now have the gradients for weight 1 and weight 2. But where have we seen these numbers before? Let us place them directly onto the weight space landscape from episode 3. Weight 1 is the x-axis of our landscape. Backpropagation just told us move negative 0.3 units along that axis. That is not an abstract number. It is a physical direction on the terrain. Weight 2 is the y-axis. The hidden node activation of 0.5 multiplied by the output error of negative 0.2 gives negative 0.1 units along the y-axis. A second independent direction. Combine them using the parallelogram rule and you get the master gradient vector, the red arrow from episode 3. Backpropagation is the compass. Gradient descent is the step. They are the same algorithm seen from two different angles. We did this calculation for exactly 2 weights. Now multiply this process across thousands of nodes and billions of individual connections. The architecture of a modern large language model. Instead of computing each gradient one by one, graphics processing units pack these equations into giant matrices. A single matrix multiplication propagates the error signal through an entire layer simultaneously. One backward sweep. Every single parameter receives its exact gradient. The architecture is fully updated, and the model is measurably smarter than it was 1 second ago. We touched on momentum in episode 3. In practice, modern networks use ADAM, adaptive moment estimation. ADAM tracks 2 quantities for every single weight. The first is momentum, a running average of past gradients, giving the optimizer inertia. The second is variance, a running average of squared gradients, which adaptively scales the learning rate. Weights that see large consistent gradients get a smaller step. Quiet weights get a larger one. ADAM is why neural networks converge reliably at scale, and it is the default optimizer for virtually every large language model trained today. You now know exactly how a machine learns. A forward pass to predict, a backward pass to correct, a gradient descent step to improve. Repeat this cycle billions of times, and you have the engine behind every modern artificial intelligence system. Next time we dive into embeddings and the latent space. Subscribe to Fromobius. Let us decode the black box together.